Okay, so I'm going to spend a little bit of time now talking about thermochemistry and thermodynamics. All of you should have at this point your at least your first image packet and materials that go with this unit. Some of you got them yesterday, some of you got them today. So I want you to think about this for a minute. Obviously, when we think about the energy of the universe, where would you tell me that most of the energy in the universe comes from? Kyle, what do you think? Stars. Can you single it in a little bit more? I can't argue with those two things. I would suffice to maybe just say, like, if we really think about this, we talk about the sun for our particular Earth. Now, we can pretty much all agree on that. If I don't think about this, and I just take that out of the equation, where does the bulk of the energy for our everyday lives come from? If I take this out of the picture, or maybe I should say the energy that we use in our everyday lives in tons of different forms is a result of what? What? How do I get that heat? Okay, so let's be way more specific. How do we have that? What has to happen for all of those things to happen? Boom, thank you. So, most of the energy in our everyday lives comes from chemical reactions. Now, I think it was Kyle that said heat. Think of some ways, even if we think about our Bunsen burners, think of some ways that we get that heat energy. You ever drive by the, what is that? The old school in Fletcher that's now like sort of a house with lots of animals out in the yard? You know where I'm talking about? You know how they used to heat that school like years and years and years and years ago? No. What did people before? Okay, so not wood, but before we had DP&L and some of those kind of things, what falls in the middle there? How do people heat? Yeah. So there's a good example of how we produce heat energy. Is it the most efficient way? No, absolutely not. But that could be used as an example. We could probably put down natural gas. People still use that to heat. What about maybe let's think about something like a flashlight. What powers a flashlight? Yeah. So we can use something like that as an example. All of those things are used to produce electricity. We could even go so far as to think about, maybe we'll switch from this heat and electricity and maybe think about our bodies, the human body. What? ATP, yep. Remember there back in bio you went through ADP, ATP, all those different things. What was it, AMP? adenosine monophosphate, adenosine diphosphate, adenosine triphosphate, all of those things provided energy for the body. Those are all part of chemical reactions. What do we use those things for? Simple things like carrying out really all of our bodily functions. Body temperature, keeping your body in homeostasis. All of those things really have to do with chemical reactions. Everything that's going on inside your body is a result of a chemical reaction. So we're going to take these things and we're going to look at them in terms of thermodynamics, which thermochemistry is a part of. So, anybody in here able to define thermodynamics? Any idea of what it is? Probably need to look at that. What do you think, Kyle? Okay. That's pretty good. Dylan, were you going to say anything different? No. So let's call this, instead of heat, let's say energy. The study of energy. I'm going to say transformations. So obviously you should know way back from your, maybe your Mrs. Gump days. The Latin roots, your therm means heat. This dynamics represents power, that part of the word. So we're thinking like heat, energy to power. Didn't really pay a whole lot of attention to this. Scientists didn't. Until something big happened within the United States. And suddenly power and energy and all of those things became important. Does that give you an idea of maybe when we started paying attention to thermodynamics? What part of American history? What do you think, Dylan? Yeah, so really, which is kind of interesting. It was during the Industrial Revolution that we started trying to, let's say, improve the relationship. And pay attention to it, really, in general. Let's say between heat energy, which we know heat is a form of energy, work, and power, and how different fuels came into play. We were finding ways to do what during the Industrial Revolution? Dylan? What? Yeah, produce things. What kind of a way did we want to find to produce things, though? We were already producing things. Mass production, we wanted to become way more efficient. So really, we're thinking about efficiency also. Now, there's a portion of thermodynamics which is called thermochemistry. We're going to spend a little bit of time with thermochemistry as well and introduce some different principles. We're going to kind of put the two together, talk about the laws of thermodynamics, talk about calorimetry, and all of those kind of things. Hess's law, many different things. So when I look at thermochemistry, I am looking at or examining the relationship between chemical reactions and let's say the energy and heat involved. So notice that all of these things include energy and looking at energy and looking at what's happening to the energy within the system, within the surroundings. Eventually we'll get to that point. So let's think back here, way back. You've been hearing this for years. What is our tried and true definition for energy in general? Can you tell me, Morgan? Oh, look at her eyeballs. No? It does have something to do with work. Good. What about work? Riley, what about work? Good job. Yes. Ability to do work. Does a chemical reaction have the ability to do work? What do you think, Danny? Yeah. So I can say that a chemical reaction has the ability to do work. When that work is done, some things happen. We've felt it in lab already this year. We've talked about it in lab already this year. What kind of energy are we generally talking about when we're talking about a chemical reaction? Yeah, Dylan. Heat energy. So we're going to think about this heat energy. We've seen two different kinds of chemical reactions throughout the year. One we see most often, one is a little less common. Bridget, do you remember what they are in terms of heat? Anybody help her? Kyle? Yeah, so we can have our exothermic and our endothermic. If I have an endothermic reaction, Hunter, what's it going to do in terms of heat? Yep, so here I have some absorption of heat. And Cadence, if it's exothermic, what's going to happen? Yep, so we'll have a give off heat. And those are going to come into play just a little bit more as we talk about thermodynamics and thermochemistry. So let's think about a combustion reaction. We've seen those before. We know what they are. I'm going to use gas plus oxygen. Any kind of gas. You can even think about gasoline in terms of this. Don't we have an engine named a combustion engine? Yeah. So my gas can expand. It can do work. If I'm talking about gasoline, what's the work it's doing? Somebody else talk to me. Morgan, what's the work it's doing? That's all I wanted. It powers the car. So everywhere in our everyday life, we have combustion reactions, we have all kinds of different chemical reactions. So then let me ask you this question. Where does the energy in a chemical reaction come from? Maybe I could say what kind? Where does the energy in a chemical reaction come from? Or what kind of energy is it? Kyle? Okay, that's a good place to start. It's potential energy. What else did you say? Yeah, potential energy, and it's stored in chemical bonds. Okay, so now it's stored in chemical bonds. Let me think of a way to say this. What type of interaction is going on in a chemical bond? What do you think, Dylan? Yeah, an electrostatic attractive interaction, right? So we have, in this case, some electrostatic interaction. Now, we've talked about this before, briefly. Where does this electrostatic interaction come from? What do I have in there? File? Oh, yay! What? Yes! Thank you. Someone answered me. I got really excited. Sorry, Morgan. I think I've done that to you twice today. Yeah, it comes from those charged particles. And if you remember back just a while ago, we talked about something called electrostatic potential, which was EL. I would say that it is associated, I'm going to break this down, with two charged particles, so we're comparing them. Two charged particles, and it is proportional to their electrical charge. remember we called those Q1, Q2, and it is inversely proportional. Anybody remember to what? No? A constant is involved. Inversely proportional to, oh, why did I write that? To the distance between them. And if you think about that, like versus opposite charges, distance between them, it all makes sense. We did have a formula for it before, and we only used it very little. It was EL is equal to K, that's where your constant comes in. Constant's the same, so it becomes not really that important in terms of using the information you get from this to apply it to different situations. So it was Q1, Q2 over V, where this is my distance between particles. These are my charges. And that was, K was my proportionality constant, which was 8.99, excuse me, times 10 to the 9th, joule meters per coulomb squared. Now, if you look at, I should have them somewhere. Yeah, if you look at this that I gave you earlier, you'll notice the first page has it on both the front and the back. It's easier to look at if you flip your first page. And it just kind of walks through what happens. If I have a smaller separation, greater repulsion, greater separation, less repulsion. We know that. We've been over it a bunch of times. If there's less repulsion, obviously they're farther away. And we also can look at like charges versus opposite charges. Are you with me? Yeah? 9. Sorry. So read through that. See if it makes sense. See if you have questions. Just look at like charge versus opposite charge. Anything on there? There's nothing new on there. It's stuff we've all talked about before. And it should make sense to you. Okay. No questions about that? So let's look at this overall then. Overall, when we look at these things, we can say energy is released when chemical bonds form. And we can say that energy is consumed when chemical bonds break. Okay, so that gives us a little look into